So I promised you reaction mechanism 7 was going to be probably the easiest thus far. And I'm just going to go right to the mechanism right now, and hopefully you'll see why. In this case, we begin with a hemiacetal. So again, when we're drawing a hemiacetal, we're going to have an alcohol functional group and an ether functional group on a central carbon atom. So here's our hemiacetal. Again, this is a reaction mechanism number 5, product. Like we saw in our previous reaction mechanism, we can begin here by protonating the group that we want to be a leaving group. This leaving group, like we saw in our previous mechanism, is not just going to leave, it's actually going to be forced out by using electrons on an adjacent heteroatom, either a nitrogen or an oxygen here, reforming a pi bond there between the carbon and oxygen atom, and now breaking the sigma bond to the best leaving group, which again is going to be the weakest bond there, to our protonated alcohol. And we're going to generate this very electrophilic intermediate. This very electrophilic intermediate is now very susceptible to nucleophilic attack by a second equivalent of alcohol, generating another tetrahedral intermediate, which is our protonated acetal product, which can be easily deprotonated by any solvent water that's around, leaving us with the final acetal product. So if you look back at the reaction mechanism that we had for number 6, taking a hemiketal plus an additional equivalent of alcohol to generate a ketal, hopefully what you'll recognize here is the only thing that's different between this mechanism and the one you just turned in today, or for reaction mechanism 6 here, is the presence of a hydrogen here on this carbon rather than another alkyl group if we began with a ketone. So not too much to comment on here. I hope you're really getting bored with these mechanisms that have this repetition. Again, this mechanism essentially picks off where reaction mechanism 5 left off, is identical to reaction mechanism 6 with the exception of a hydrogen coming in the place of an R group because we started with an aldehyde instead of a ketone. Again, this nucleophilic addition reaction, having a nucleophile, having a heteroatom, either a nitrogen or an oxygen from an amine or an alcohol here, those lone pair of electrons are going to allow this chemistry to continue to do nucleophilic addition elimination chemistry by eliminating that functional group that we protonated to make it a good leaving group. Again, just like we've seen in the rest of these mechanisms in this 4-part series here, we've got a very electrophilic or reactive intermediate that's going to react with that second equivalent of alcohol to generate the acetal. So the last thing to just kind of highlight with this mechanism is how this kind of probably occurs in a way that you've seen with organic chemistry. When you have a diol of sufficient size, that means you have 2 alcohol functional groups within the same molecule. We can use that to protect a carbonyl containing functional group like an aldehyde or a ketone. So I'm just going to kind of show that here. So for example, if we have this aldehyde or this diol here, and again, this is specifically chosen because it will form 6-membered rings. And again, I'm just going to kind of highlight with my laser pointer here how this chemistry would happen. We'd have 1 equivalent of alcohol nucleophilically attacking this, generating an alcohol at this position and generating our hemiacetal. And then because we've chosen a system that can form six-membered rings, this second alcohol equivalent is going to be within the proper geometry to have proper orbital overlap and do the second equivalent of alcohol addition, now at the same carbon atom. And so the product that we're going to get from the first addition is going to look like this. And again, because we have the ability to protonate this guy, make him a good leaving group, the lone pairs on this oxygen atom will allow this guy to leave, generating a very electrophilic intermediate here. But because we are within 6 atoms, we are going to be able to have an intramolecular nucleophilic attack here to generate our final product. And so the final product here that we have is this guy. And so this is often how you will protect carbonyl-containing functional groups in organic chemistry. So whether you have an aldehyde like we see here, or you have a ketone, using either a diol with 3 intervening carbons or 2 intervening carbons, which would give you the 5-membered ring here, those intramolecular reactions like we'd happen right here happen quite easily. Intramolecular reactions are always faster because you have a higher effective concentration of your nucleophile here. But again, these intramolecular reactions are only going to happen when we have atoms that were within 5 or 6 bonds away to allow for the best orbital overlap and the least angle strain.